Hey everybody, so this is a review for period 3, but new to period 2. We didn't have a chance to go through and talk about this before. School was closed, so we'll go back and review. Our topic of study right now is exponential growth and decay, and this graph here is our graph of what an exponential growth equation looks like. And that's our equation right here that we have graphed. A few things important to note about this equation. Yes, it is a function. Y is equal to 2 is our base. And that is our factor that is repeated in multiplication over and over x times. So what I want you to think about is that x, when we talk about an XY ordered pair chart, that X is in the exponential position. That's in the position of the exponent. So it's interesting when you look at different ordered pairs that are on this graph of this exponent. One of the most important ones that you'll see is C is an input of 0 gives an output of 1. And you remember that anything to the 0 power is equal to 1, which is why this point is going to be a constant in all of the exponential graphs that you look at. Just like every other equation, we want to always take a look at our graphing calculator and enter in that equation so we can see. So we can have 2, and your exponent key is going to be this one here, that little caret to the x power. And then when we go ahead and take a look at that graph, I had my settings on something old, so we'll do zoom standard. And there we have our coordinate plane. And you can look at interesting things you can see about this graph is that there's nothing going on down here as a negative output. And that's an interesting thing to look at here. And I want you to think about what happens when x gets really big. My value of my function gets bigger and bigger. When x gets small, then we can look at what happens when it goes negative, and whether or not this graph actually ever crosses that axis or not. We can go to the table of values, and if we go up into the negative values, you can see my values of x are getting smaller and smaller and smaller, but never going smaller than 0. So think about what that negative exponent means and what that does to the value of your fraction. It's never going to make it negative, just smaller and smaller. All right, so as we look at these critical points, I know anything to the 0 power is 1. I know that anything to the first power is itself. When I look at A, I can see I'm talking about 2 to the second power has an output of 4. When I'm looking at D, I know that 2 to the negative first power, and we can show what that looks like. Y is equal to 2 to the negative first, which means that this means I'm dividing by 2 one time. So of course, that's going to give me 1/2 as a value, and to the negative second power, I'm going to have an output of 1/4. And it's interesting how, as if I went smaller and smaller, I'd have an output at -3 of 1/8. And I can see an asymptotic relationship where it's going to approach the axis, but it's never actually going to get there. Okay, so I read a story and I recorded it for you. 1 Grain of Rice is a great mathematical folktale, a story of exponential growth. We want to remember that x is the input and y is the output after that exponential growth. And there's a cool chart at the end of the story. So I posted a link to me reading a storybook. So if you need a a good story. There you go. All right, so what we want to talk about is the value of y when x is positive is that it grows exponentially. The value of y when x is 0, it's always going to be 1. The value of y when x is equal to negative, it is a small fraction, a value that is between. It's going to be smaller than 1, but it is also going to be bigger than 0. All right, so when we look at these notes, we begin to look at the structure of our equation. Graphs that have x as the exponent are called exponential functions. And that a represents that same kind of coefficient that could make our graph get bigger faster or bigger in a slower rate. Exponential functions will always have a horizontal asymptote where it'll approach but never reach 0. And we're going to talk about this value of b. What happens with b? If b is greater than 1 or the graph is going away from the asymptote, we're going to call that growth. If b is between 0 and 1, this value here, our base that is being raised to that exponent, if it's between 0 and 1, or if it's moving towards the asymptote, we're going to call that decay. All right, so this link here is talking about real-world growth. I posted this link, and what's interesting, it is the prediction of our COVID-19 situation, our current pandemic, but it was their view of things on March 6th. So it'll be interesting for you to watch that video and see the story of how that exponential growth was used to form the models and the instructions that we as Virginians and Americans went ahead to try to flatten the curve and try to change what that exponential outcome had left us. We did not get to see March Madness this year, but if we had, you would have had an example of real-world decay. The NCAA tournament starts with 64 teams, and each time that we have a round of basketball, we eliminate and come on down. So two forms of this equation we can talk about. It's going to be y is equal to, and you want to talk about 64 is what you're starting off with, and each time you're multiplying it by 1/2. So if you take a look at my input being x, 0, that makes this equal to 1. So that's 64 times 1. I've got 64 teams. If it's 64 times 1/2, 32. 64 times 1/2 squared, that's going to give me 16. So we can look at this input-output table as far as whether we're talking about which round of the basketball and our number of teams that's left. Our second format of this equation, and I want you to think about this, play with it on your calculator. We're still starting off with our 64 teams, but let's talk about it from the opposite perspective. So anytime I look at the relationship between 1/2 and 2 and my positive and my negative exponent, these two graphs are both going to give me this decreasing relationship, and they're both going to give me this input-output table. If you don't believe me, try your calculator. All right, so when we flip the note page over, when you look at each of these and consider, I just want you to get your calculator out and let's take a look at each of these stories. So I have here, I'll go to my y is equal to, and I'm going to have 3 to the x power. When I go to look at my table of values, I want to try to look at positive, negative values, and 0. because that's going to give me a full picture of what we have going on. So, of course, anything to the 0 power is 1, and anything to the first power is itself, and then 3 squared is 9, and 3 cubed is 27. But then we can look at each of these examples, and a -1 as an exponent, of course, is going to mean that we are dividing by 3 one time, or 1/3, or that's the same as 0.33333. This 1/9, of course, is the same as 0.11111. When we go to look at this example, we can see anything to the 0 power is 1. Anything to the first power is itself, 1, 2, 3. Anything to the second power, 1, 2, 3, 4, 5, 6, 7, 8, 9, is going to be where that big change happens. Because a 1 and the value of itself is one thing, but then we can see this huge curve going up and getting so high so fast. The great part is taking a look at what happens on this side. So when I have an input that's negative, my output is positive. An input that's negative means I'm dividing by 3 2 times. That's my 1/9. And of course, this is going to be 1/27th or 1/81st. So we end up with what's called an asymptotic relationship. The graph approaches the x-axis, but it's never going to cross it because I'm not going to get an output that's negative. Now, when we talk about this, my b is my 3. And my b here was greater than 1. And that's what represents that growth, my base. When we look at this next example, we're going to see here that my base, my factor that I'm multiplying again and again, is 1/3. And that 1/3 is greater than 0, but it's less than 1, which is going to give us an example of exponential decay. Anything to the 0 power is itself. Anything to the first, or anything to 0 power is 1. Anything to the first power is itself. And then here's 1/3 when it's squared. But let's take a look at what happens when I have a negative exponent on a fraction base. So we'll come over here and we'll go ahead and we'll use our parentheses to make sure that we end up with 1/3 to the x power. Take a picture or take a look at the picture of it, and we can see instead of like growth where it's going up, now with decay it's coming down. When we go to our table of values, there we see some numbers we recognize. Look at those nice whole values. -1 goes in, 3 comes out. -2 goes in, 9 comes out. Because that negative exponent has us use the reciprocal. It has us flip. So then when we go to graph this, we can look at anything to the 0 power is 1. That same graph applies. But now we have over -1 up 1, 2, 3. Over -2 up 1, 2, 3, 4, 5. And you'll notice that here, that exponential decay is going to take an opposite reaction, 1/3, 1/9, and so on, where I approach but don't ever cross that last asymptote. Here is our example of growth, and here is our example of decay. So we can see as my graph moves from left to right, my output is approaching my asymptote. As my graph here moves from left to right, my output is approaching infinity. All right, so for these two examples, we're going to look at the graph and we can see whether it's growth or decay. And it's harder here because we don't have the equation and we don't necessarily see what's going on, but we can go back to our conversation about whether it's moving towards or away from the axis. If it's growth, it's moving away from the axis as you go left to right. If it's decay, it's moving towards the axis as you move from left to right. So when I look at my growth, this being away, it looks like it's just a negative graph of this. So here, if you picture this graph flipped over, then you can see that this is growing away from the axis. So this one is definitely growth. When we have here, as I move, again, talk about what you're doing from left to right. As I'm talking about left to right, this graph is moving up and getting closer and closer and closer, which means this is a great example of a exponential decay. It's getting smaller and smaller, moving towards the axis. Okay, so here we have a basic format that I know you remember because it's very similar to what you've seen in the past. So you're used to seeing something like this, where we have x minus h, and then we have k, and we recognize that maybe this is plus or minus, depending on how it's going. And maybe this is an exponent, depending on if it's a quadratic or cubic. We've also seen our absolute value bars. But you'll notice the same customers are here. Here's my H and my K. Here's my A. So when we talk about the value in each of the parts of the equation and what that means, A is again always going to represent our stretch and our compression. And remember, if it's negative, it's also going to talk about whether or not we have a reflection. When we look at B, B is always going to be our base. And our base is that value that is multiplied repeatedly. Now when I have my H is going to again always talk about my left-right shift. And I want you to keep in mind, remember that that value is naturally negative. My K is always going to be my up-down shift. And remember, my vertical shift is always true to sine. So when we're talking about each of these graphs, this H value is going to move it left and right. This K value is going to move it up and down. And this A, whether it is a value that is positive or negative, is going to tell you whether your graph is upside down or not. Our base, I want you to still remember the rules about if your base is greater than 1, it's going to be growth. And if your base is between 0 and 1, then that's when you have exponential decay. For all of these values, our domain is going to be all real numbers. You can put any number you want into this function, but your range is typically going to represent your asymptote to infinity. So you're either going to have it approaching 0 and positive infinity if it's growth. And don't forget, you might have to either plus or minus k, depending on what's happening. If it's decay, you're still going to have that same scenario, depending on whether or not there's a reflection. If you have a reflected value, then you're going to have a negative infinity up to, but not including, of course, your asymptote. and whether or not that's 0 plus or minus whatever your k value did. Okay, so the next page is some practice pages. Go ahead and take a look at those problems and work it out on a separate piece of paper or on the note paper and check back in for your answers.